If you're losing marks on coded values questions, you're probably slipping up when following one of these iron rules for dealing with them. And that's especially true if you're doing CIE 9709 paper 5 and the sum of x minus a squared questions just aren't really clicking for you. So here are the 5 rules that cover every single coded values question Cambridge can throw you. Okay, so to explain this, let's give a running example which we can use for all the rules we're going to cover. Let's consider 5 data values: x equals 10, 12, 14, 16 and 18. Okay, so obviously here our n is equal to 5 and the sum of all these values is equal to 70. Okay, sum of x squared, that's going to be 1020, and the mean, therefore, sum of x over n, that's 14, and when we work out the standard deviation of x, that's going to equal 2.83. Okay, so why am I telling you this? Because this is a representation of our values at the moment, but what if we want to make things a bit simple for ourselves when dealing with data? Well, that's where we start to code values, okay, just to simplify it, just to make things easier for ourselves when dealing with that data. So what we're going to do, guys, is we're going to code this data using y is equal to x minus 10, okay, and for some rules as well, we'll use y is equal to x minus 10 over 2 to illustrate the different rules. Okay guys, so for rule 1, okay, it's pretty much, as you can see, simple shift coding. Okay, so this is where our mean changes. Okay, so as you can see, we've got y is equal to y bar is equal to x bar minus a. Okay, so therefore we can say that x bar is equal to y bar plus a. Note here that the standard deviation is unchanged. Okay, so I'm going to represent that with an example now. So let's say in this example, okay, that we're going to code, say, rule 1. Make that a little bit bigger, actually. Okay. Rule 1. Okay. We're going to code with y is equal to x minus 10. Okay, so that means for each one of these values we're going to alter them somehow, and since our code is y is equal to x minus 10, okay, what that indicates is that our new coded values, or just coded values should I say, well, that's going to equal 0, 2, 4, 16, or better yet 6 should I say, and 8. Okay, so all we've done here is we've just made it a little bit easier for ourselves to deal with the issue, with the problem at hand. Okay, and so what happens now? We've got sum of y. Our sum of y, we can simply say, is going to equal 70, okay, minus 5 times 10. Now why is that? Because as you can see from the rules, okay, the sum of y is going to equal the sum of x minus n times a. So as you can see, we've made things a lot easier for ourselves. Instead of having to calculate everything on its own, which can be inefficient, what we've simply done is we've applied the rule by saying, okay, sum of y is equal to sum of x minus na. And as a result, we've got sum of y minus, sum of x minus n times a. Okay, perfect. So as a result, it's going to give us 20. Okay, remember n is staying the same here, so we're going to say that our y then, our y bar, is going to equal 20 over 5, which equals 4. Okay, What does that mean? It means our original mean then, so our coded mean is equal to 4, and our original mean now is going to equal to 4 plus 10, which equals 14. Okay, so as you can see, we've clearly illustrated here that rule in action. What is that rule? That the original mean is equal to the coded mean plus a. Okay, now know what happens here. Note something quite important. That is that the standard deviation, okay, of y. What is that? Well, the standard deviation of y, you could go through and calculate that, but according to our rules here, it's simply going to equal 2.83. Now, why is that? Well, that happens because all we've done here, guys, is we have shifted our values. We haven't scaled them. So as a result, the spread hasn't changed here. It's stayed the same. So as a result, all we've done here, okay, is we have very much just altered the shift, but the spread stays the same. Okay, so that's why standard deviation here is unchanged. Obviously our mean, our coded mean changes. Okay, so shifting doesn't touch the spread. We've established that. Okay, so as you saw before, our standard deviation was unchanged. But what happens now if the examiner throws a curveball and we are dividing by number 2? Okay, so that's where things can get a little bit tricky, because now we've got two things changing at the same time. And if you don't know which one affects what, you can get the wrong answer, and that's not fun for anyone. But I must stress, the key thing is these are not exam style questions. This is all just to kind of demonstrate and show you a bit of an understanding behind how coding works, so that you can kind of apply some principles to solve whatever question is thrown at you. If you want some more stuff, I've got a link below, but let's just focus on this for now. So, okay, now we're shifting and scaling. Okay, so what does that mean? So shifting and scaling. Okay, so all that's going to happen here, okay, is our coded mean y is equal to the coded mean is equal to our original mean x minus a. Okay, we're shifting, fine. But now we're going to divide that by b. Okay, and so therefore if we rearrange that, we're going to get our original mean equaling b times our coded mean y plus a. Okay, and with the standard deviation, unlike before, this time there's going to be some kind of change happening. Why? Because this time we are scaling. Before we were simply shifting, and because we're scaling, the standard deviation is going to scale. It's going to scale. What am I saying? It's going to scale also. Okay, so our coded standard deviation y is going to equal to our original standard deviation x over b. Okay, so therefore our original standard deviation x is going to equal to b times our coded standard deviation. Okay, and that's one way of looking at it. Sometimes what the examiners will do is they oftentimes use this notation. Okay, and they'll say mean of y, which in our case was just y with the bar on top, is equal to a mean of x, x bar plus b. Okay, we did the same thing. We did the same thing here. We just changed x and y around, and they did a similar thing for standard deviation and variance. So don't get confused about the notations. All you need to know that the principles, that's the most important thing here. Okay, so it's all well and good me showing you the algebraic notation, but it's actually again understanding of how shifting and scaling actually works. Let's go back to the example. Okay, so here we are, guys. Same example as before. We've got 5 data values. Perfect. And we've got our, the values that were pre-calculated for us. Now again, I must stress this is not an exam style question. This is simply just to get an intuitive understanding behind the rules that are going to help us to kind of decipher the questions, the more harder questions when they come to us. Okay, this is just for intuition, really. So this time we're shifting and scaling. Okay, shifting and scaling. So as a result, that means what? Well, y is equal to x minus 10 over 2. So what does that mean our coded values become? Well, coded values, if we apply y is equal to x minus 10 over 2, well, 10 minus 10 over 2 is 0. 12 minus 10 over 2 is 1. 14 minus 10 over 2 is 2. 16 minus 10 over 2 is 3. Okay, and lastly for 18, we're going to get 4. Okay, so these are our new coded values here. Okay, and again, what coding comes down to is just changing the way the data is represented to make things easier. On a wider scale, in like business applications, etc., it's used to just simplify things. Because if you've got data that's very messy to work with, this can be very helpful. Okay, so from this, what can we say? Well, we can say that the coded mean, okay, we know that the coded mean is equal to the original mean as A over B, which means our original mean, well, that's going to equal 2, okay, 2 times our coded mean plus A. Right. Now we were already given the original mean. That's not the point here. The point is to decipher. Okay, so if we look at this now, we add these up. We're going to get 4 plus 3 plus 2, 7, 9, 10. Okay, we're going to get 10 over 5, which equals 2. Okay. Therefore, our coded mean, guys, is equal to 2. Okay, and what's A? Our A is equal to 10, because that's what we shifted by. Okay, so therefore, applying our formula, okay, we can say that our original mean is going to equal to 2 times 2 plus 10. Okay. Equals 14, which is what we were given from the get-go. Okay, so again, this is not like an exam question, it's not even like a practice question, it's just to give you an understanding of how this all works. Okay, so pretty simple explanation there. And what about the standard deviation? Okay, well, the standard deviation, give that a green highlight. Standard deviation of our coded set now, well, what's that going to become? Well, it's the sum of x squared, right? Or y squared, should I say, over n. Okay, and it's going to be minus coded value squared. So if we do that, okay, 4 squared plus 3 squared plus 2 squared plus 1 squared, that's 30. Okay, it's 30 over 5 here. Okay, minus 4, because remember our coded mean here was 2, right? So then there, we put that in our calculators. We get root 2 equals 1.41. Okay, but we're not done yet. That's our coded coded standard deviation there. Now remember what our formula is. We know that coded standard deviation is equal to our original standard deviation over our scaled factor. Okay, so therefore our original standard deviation is going to equal to times the scale factor there times the standard deviation of our coded set. So therefore standard deviation of x, our original standard deviation that is going to equal to 2 times 1.41. Okay, why 2? Because remember we divided by 2 in the beginning, right? So therefore we get 2.83 there, or 2.82 even. In fact, there, 2.83. I should just get this as root 2. Okay, for our final calculation. So use root 2 for the final one. Sorry, that was a mistake on my part. So use the, let's change it to root 2. Okay. So as you can see, guys, what's happened? What's happened here? Well, our standard deviation, okay, our coded standard deviation has effectively been halved. Okay, it's been halved because we scaled by a factor of 1 over 2 here. So, evidently, unlike the example before, over here, scaling makes a difference. Okay, that's evident. And at the same time, we used our values here, okay, with some new kind of formulas to basically backtrack and work out what our original values were for the original mean, original standard deviation, given our coded values. So that's quite an important skill to know.